Hello.
Hello, Daniel. How are you?
I'm right. How are you?
Yeah, good, thank you. So, shall we do these questions here?
Yeah. Just a second. I'm just gonna go get my book. I have a few questions from my book I need to
Okay.
have.
Okay. Yep.
Okay. All right. I'll screenshot them and send it to you now
Okay.
on my online textbook
On Facebook.
on Facebook. Yes. I'm just gonna get them from the textbook
Okay.
online. I have my exams on Thursday, so I've also booked tomorrow if that's okay.
Yeah, sure.
All right. I've sent it to you.
All right.
It's loading.
This one here.
Yep. This one.
Okay.
It has to use I looked at the answers. It has to use limits, and I don't know how to do that.
All right. So the life x hours of a type of a light globe has a probability density function like that. So that means every single one of them has a lifetime of more than 1,000, doesn't it?
Yep, that's true.
So the function will look like this. So this is 1,000 here. And this is absolutely just a 0.
Mm-hmm.
And then it's a k over x squared. But k over something over x squared looks like this,
Mm-hmm.
if that's positive. So it's kind of going like this, and then starts from here, and then go down like this, right?
Sure.
So this whole area has to be 1, but there is no upper bound. The upper bound is infinity. Just goes on forever,
Mm-hmm.
But obviously the lifetime can be infinity, but of course the probability for that approaches 0. So you just need to find integral k over x squared, and then you simply have to write 1,000 here,
Mm-hmm.
and then you cannot put infinity here, right? That's the problem. So we put b here, and then we say limit b goes to infinity later.
Okay.
And that's how you figure out the k value. So this is known as improper integration.
Sure.
Improper integration.
Yep.
So this one here becomes, this is a limit of a b goes to infinity, integral 1,000 b, and then you have k x minus 2 dx. So this one becomes x to the power of -1 or -1, so that's negative k. That's the integration. This is b here. Therefore, what does this become? You plug in b, then you get negative k over b minus negative k over x, so that's equal to 1,000, like this, and this has to equal to 1. So this one is positive k over 1,000 minus k over b. Actually, I forgot to put limit here. Limit. And then this is a limit as well. And so from here, as b goes to infinity, you can see that this term becomes 0, doesn't it? And this has to equal to 1.
Okay.
So you get k over 1,000 has to equal to 1, so k must equal to 1,000. Is this the correct answer?
Let me just check. It is question 13. Yes. No. K. Oh, yeah. K is equal to 1,000.
Yeah.
Sure.
So if I do this from 1,000 to about 9999999, if I do that, gives you 1, doesn't it?
Yeah.
Yeah. Okay. So find the probability that the light bulb will last at least 2,000. That means you just have to integrate this from
2,000.
2,000. Yeah, 2,000 to
1,000.
no, infinity.
Oh. Okay.
Just start from 2,000. That's it.
Okay.
So that's 50%. So this is 1,000 here, but this is at 2,000. All right.
Mm-hmm.
And you integrate that from 2,000. So at least 2,000 means more than 2,000, right? So you integrate from 2,000 to infinity. That's what you have to do. Okay.
Mm-hmm.
Yeah. But obviously, you cannot use calculator for that one. You have to use the same thing here. You have to do limit of a b goes to infinity. Here, b here, and then 2,000. And then k over, so this is 1,000 here now, right? 1,000 over x squared dx. So you need to actually prove that this is 0.5 exactly.
Mm-hmm.
Now, next problem. Did you send something else?
Yeah, sure. Wait, hang on. Can you just quickly go back to the board,
Exam?
please?
No, the board, okay.
Mm-hmm. So can you have a look at how the limit this middle of the screen where you have 2k values?
Yeah.
Yeah. So how do you so you have two variables two negative k's. How do you determine that k is how do you get rid of two variables in this situation?
Okay, so what I did here was there's a limit here, and then once you integrate this bit here, is that right?
Mm-hmm.
Then you get this one here.
Mm-hmm. Yep, that's easy. Yeah.
Mm-hmm. And then you plug in b here,
Mm-hmm.
1,000 here.
Mm-hmm.
Because x to the power of -1 is the same as 1 over x, right? So this is over x here like that. You plug in b here, plug in 1,000 here.
Mm-hmm.
Then you get this. And you still have the limit, right?
Mm-hmm.
But then so I just switch these two around because that's positive. Negative, negative is positive, right?
Mm-hmm.
So that bit there becomes this one here.
Mm-hmm.
And
Yep.
that bit there goes over here.
Mm-hmm.
And then I apply the limit. Okay. All right, apply the limit, which means b goes to infinity. So k over infinity is actually 0. Any constant over infinity is what?
Mm-hmm.
0, isn't it?
Mm-hmm.
Therefore, that's 0. So, but that has to equal to 1, doesn't it? So that's why this bit here, that's this blue bit, that has to equal to 1.
Yep.
And you get k equals 1,000.
Yep, sure. All right, I'll send you my next question.
Mm-hmm. Done?
Oh no. Yep, that's it. That's all the questions.
Okay.
Wait, hang on. No. One more.
Haven't received yet. Did you send it on Facebook?
I haven't sent it yet. I'm trying to find one. Okay. Yep, sent.
All right. You sent the same thing.
Oh.
Should we just go through the exam paper here?
One more question. We'll go for it. Sorry. One more. Okay, can you check that again, please?
Yep.
Okay.
It says continuous random variable acts as the
this
probability.
graph.
Yep. Sorry, say it again.
Yep. So it's from 0 to 1.
Yeah, 0 to 1. So this one is the parabola starting from here, and then it goes like this, and then 1 here, and then 0 here. So it's just that area.
Oh, no. I sent the wrong question. Whoops.
You sent the wrong question again.
Yep. Sorry. There we go. I'm sure now.
Yeah. Okay. Okay. So you need to sketch this graph. Is it right?
Mm-hmm.
And that's pretty simple.
Mm-hmm.
Because you know what e to the x looks like, do you?
Yep. It's like a.
It's an exponential function, isn't it?
Yeah.
But it is, so it's a positive exponential function.
Mm-hmm.
Is from x is less than 0, less than or equal to 0. So it would actually look like this, right? But then you only take the negative side.
Yep.
The other one is just a mirror image of this with respect to the y-axis or x-axis.
With
the
respect
negative
to the y.
y-axis. So it would look like this, but then we only take the right-hand side of it.
Okay, sure.
Yeah. So they are saying that this one has area of 1 because it is a probability density function, isn't it? We don't have to prove that. They already just say that this is a probability density function, so we just have to trust it. So it's find the interquartile range of x, giving your answer correct to 3 decimal places.
Which equation do we integrate in this case?
Well, they look symmetrical, don't they? So I need to find this value here, I think, where, so if interquartile range is from A to B, true? But I think this will be a negative B, I think. If this is B, this will be negative B. Because it's symmetrical. So you can write, since function is even means symmetrical against the y-axis, we can find B such that integral from 0 to B of the f of x dx equals to 0.25. Understand? So we find B so that this area here is 0.25. Then this will be 0.25 here, and this will be 0.25 here, and this will be 0.25. True?
So it's just double.
Yeah,
B.
and interquartile range would be negative B to B. You understand?
Yep.
So that's how you do it. So integral integral from where to where?
B to negative B.
No, if you do B to B,
Oh, we
then
can just
that'll
do
be
B to 0. Yeah.
we just
B,
need to. This is a lot easier, no?
Yeah, B to 0.
To B, because if you do negative B to B, you have to separate that into two functions.
Two functions.
You have to integrate negative B to 0
Mm-hmm.
with this function here, and then 0 to B with this function here. See?
Mm-hmm.
So why do both of them when you can just do one of them? You know.
Sure.
So 0 to B is going to be this negative function here, 0.5 e to the power of negative x
Mm-hmm.
dx, and this one is going to be. We want this to be how much?
0.25.
0.25, and this is very easy. 0.5 e to the negative x over negative 1.
Mm-hmm.
That's how you integrate it, and then 0 to b
Mm-hmm.
is equal to 0.25, right?
Mm-hmm.
So plug in b there, plug in 0 there, you get negative 0.5 e to the negative b, minus plug in 0, you get negative 0.5 e to the power of 0, is equal to 0.25. This one here is negative 0.5 over EB
Mm-hmm. Plus
0.5,
0.5.
negative 0.25, right?
Mm-hmm.
So you get negative 0.5 over EB.
Wait. 0.5. 25. There's no negative.
Yeah, that's right. No negatives. So 0. Yeah, this one is equal to
Negative 0.25.
negative 0.25 plus plus, and you swap this one and this one. So you get 0.5 over 0.25 is equal to e to the power of b. So you get ln b is equal to, hold on, not ln b.
ln 2.
Yep, ln 2.
Which is 0.693.
Is equal to b.
Yep. Which is equal to 0.69.
Yep, that's 0.69. Is it?
Yep.
Yep, so that's the answer for b.
Hang on. But that's B. But
interquartile range is distance from interquartile range is negative b to b. So it'll be negative 0.69 to 0.69.
Oh, okay. Yep.
Yeah. It'll be from here to here. Now, one more question from textbook?
Sure.
I think we should. Have you tried this exam paper yet?
No, I haven't had the time.
Okay.
We got it yesterday.
All right. I can send you some more questions.
Yeah, that would be good.
Did you send something else? Hello, Daniel.
Hello?
Yeah, just got disconnected a little bit.
Oh, okay.
Have you sent another question?
Yes, I have.
All right, can't see it on this one here. Let me try to refresh. Oh, don't worry. Is it this one here?
Yes.
Okay. So it is a continuous random variable again. This continuous random variable has this probability density function 0 to 3, 3 to 6. That's a straight line. That's another straight line. Sketch this graph. K is a constant. Okay. So it is only defined from 0 to 3, 0 to 3, and 3 to 6. And let's have a look at this graph here. This one is a straight line that's going downward, isn't it? But it definitely must go through 3 here, because if I plug in 3 here, then it's 0, isn't it? So I believe that it's going to go like this, the straight line, like that. And the other one is also a straight line passing through 3. So it has to go like that. Okay?
Okay.
Yeah, that's a negative gradient. This is positive gradient. So it should be like that. So it says find the value of k. That's very simple, because if I now let x equal 0 here, while x equals 0, then this value here is 3k. And if I plug in 6 here, you can see that if I plug in 6 into this line here, I also get 3k as well. So this one and this one are on the same level. Yeah, and obviously this line can go down like this, and we'll hit negative 3k. But now, we need to figure out this area, true?
Yep.
And that has to be equal to 1. So we write down, all right, this is just half times by 3 times by 3k. But then this must be the same area as well, 3 times by 3k times by half. So it must be times by 2.
Equals 1.
Yeah, this has to equal to 1. So 9k equals 1, so k is equal to 1 on 9. So k is equal to 1 on 9. Now verify that the mean of x is 3. The mean of x is 3. So we just find the average value, true? So expectation value of x is given by integral of x, f of x dx. Is that right? Do you know this formula?
Yeah, I do.
So we need to separate this into 2 parts, 0 to 3, x, f of x dx, plus 3, 6 here, x, f of x dx, because we have to use separate functions for 0 to 3 and 3 to 6 there.
Well, they're symmetrical, so we can just double it again. Can we?
Don't think so. No, they will be different.
Okay.
Yeah. So when you are figuring out just the area itself, because area is always going to be positive. Sorry. I should have muted. Sorry.
No, you're right.
Yeah, so when you're figuring out area, you can just simply double like that, okay? But I think in integration, this is 0 to 3 and 3 to 6 of this completely separate domain, so you cannot double it.
Okay.
So I show you the reason why. For example, so there are a few reasons why you cannot double it. The reason is because there is this extra term here.
Yeah. That's what I was thinking.
Yeah. So now we can write this one as x here, and f of x is at k. We already found k, right? And then 3 minus x. Integral 0 to 3 dx. This one's also k x minus 3, 3 to 6 dx. Understand?
Yes.
Still there? Yep. So you can take out the k and then expand this one out. So it's a k. I'm going to just pull out k from both of this. And it's integral 0 to 3, 3x minus x squared dx plus 3 to 6. This is x squared minus 3x.
Yep.
Yes. So there is something you can do about this one here. You can, yeah, I think it's just so there's too much risk to combine them. So I'm just going to do them all separately. 3x squared on 2. So k was 1 on 9, wasn't it? Yep. So we plug in 3 there, 3 there, 0 there, 0 there. If you plug in 3, then it will be 27 on 2 minus 27 on 3 minus 0. If you plug in 0 there. The other one is 6 to the power of 3 on 3 minus 3 times 6 squared on 2 minus plug in 3 there. Then you get 27 on 3 minus 27 on 2 as well. But interestingly, 27 on 3, this will cancel out. This one and this one will cancel out as well. No. Do they cancel out? They don't cancel out.
Yeah, they don't.
That's a negative here, negative here. So they don't cancel out. That's positive here and positive here. So yeah, that's all you have to do for this. You can also figure out the variance. So it takes a lot of time, right? I'm just going to do it here in my calculator. So integral of x bracket. So if you are allowed to use graphics calculator,
Yes, we are.
You can just skip all these steps. 0 to 3 plus integral just x bracket x minus 3 bracket, and then from 3 to 6. I just do it without k. Once you do that, you get 27 times that by 1 on 9, which is divided by 9. This whole thing will be just 3. Okay? Yeah, so the average is 3. That makes sense because you see that, you know, if you look at this area here, what's the middle point? It's symmetrical around 3, right? So average must be 3. In this case, median is 3 as well.
Sure.
Variance is you need to do it this way. So you go back to the calculator here. All right, and then you have to times this one by x squared. See, that has to be x squared and then f of x, right? And then this must be x squared as well.
Sure.
And then you calculate this. And then, of course, times that by 1 over 9. Then you get that. So what I did there is the variance is expectation value of x squared minus expectation value of x all squared. So this one is integral of x squared f of x dx minus 3 squared, because we already calculated this one, right? So this one is a 0 to 3 k x squared f of k x squared 3 minus x dx plus 0 to 3 k x squared what is it, x minus 3.
Sure. Yep, makes sense.
So if you, and then you have to do minus 9, this bit here. So what I did in the calculator is, oops, what's going on? It's an error. Anyway, I think it was 27 on 2 or something. Yeah, so it was integral. You can put everything in here, 1 on 9. Then x square bracket 3 minus x, close the bracket, and then 0 to 3, and then plus integral 1 over 9, and then x square bracket x minus 3, and then from 3 to 6. That's 27 on 2 indeed. So that bit is 27 on 2 minus 3 square. So I'm going to minus 9. Then I get 9 on 2, which is 4.5.
Yeah.
So the standard deviation is square root of 9 on 2, which is 3 over square root 2. Okay? That's how you get the standard deviation. Yeah. So obviously, if you go for 2 standard deviation, for example, then you get 95% confidence interval or something like that, right? So we know that the mean is 3. And if I go for twice the answer was this guy here. Actually, hold on. Answer was 9 on 2. Yeah, if I do that, I get this one here. So if I go for 3 plus 2 of the 2 standard deviation, then I get this one, 3, blah, 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 right? So if I integrate from here to over here, okay, which is 3 plus 3 root 2, and figure out this area here.
It will be 0.95.
Is it? Yeah, and I have to figure out this area as well, true? But I can simply figure out this area and then double it.
Yep.
So if I just go for integration from of a 1 over 9, of course I can just use triangle area, no? And then this function here, 3 minus x minus 3. So it is x bracket x, yeah, x minus 3. And then if I integrate from 3 to 3 plus 3 root 2, that's not right. So x minus 3, 3 root 2. What's a 3 root 2? 3 plus 3 root 2. That's more than 6. Sorry.
Yeah, that's 7.
Yeah, but this is just an approximation, you know. 3 over root 2 is that much. 3, yeah, that's actually too much, isn't it?
Yeah.
Times by. Anyway, in this case, it doesn't work. But anyway, that's the answer. Okay. But normally, within 2 standard deviation, you get 95%. So this is the reason why this is not working is because that rule sort of applies when the distribution is symmetrical.
Normal distribution.
Normal distribution, yeah.
Yeah.
But this is not like normal distribution at all. That's why it's not really working. All right. What should we do next? Shall we go on to these questions here?
Yep. Practice test.
Or do you want to
Hey,
try
John,
this on your own? Sorry?
I can't really hear you. I can't hear you. Can you hear me?
I can hear you, yes. Hold on.
Okay, don't worry. Yep, I can hear you a bit. It's a bit lagging. It should be
It's a bit laggy, is it?
fine.
All right, let me change some setting. Yeah, I guess the internet speed is a bit problem. I'll connect to this one here.
Okay, sure.
It might be a bit faster now, but let me know if it's a bit laggy again, all right? How long
Okay.
was it laggy?
Your sound went really kind of like an echo.
Right.
Properly, yeah.
Is that all good now?
Yeah, I can hear you now. No worries.
All right. So these are your Bergman questions, but there's also some other practice questions I can give you.
Sure.
But do you want to go through these first?
No.
You want to try them later yourself?
Yeah.
Okay.
Actually, can't find the tests at the moment.
Can't find what test?
The exam from last year.
Okay.
I don't think my teacher put it up. He put the solution, not the answer, not the test.
All right.
Which is annoying.
Okay, so there is this mid-unit test, which is, I think, about... So it's not really these stuff. There is another test, which is final abbreviated. Yeah, this stuff here. So we're going to look at these questions here. Have you tried these questions before? I think you tried this one during summer course, right?
No, I don't think.
No?
Oh, I can't remember.
Okay. There's another question like this. So we're going to try. So I'll leave all these multiple choice questions to you, okay? Let me just ask you this. So do you need to know probability? So let's just consider this question here, question 1. Which one of these is a valid probability distribution?
So they have to add up to 1. So 5, 7. I'll say 1 and 2.
So 1 and 2 are fine, is it? But 3 is definitely not okay because probability can never be negative.
Yep.
So they all add up to 1 and add up to 1 here, right? 4, 5, 7. Yep, that's good. So 1 and 2, very good. So you know the distinction between discrete random variable and continuous random variable?
Yes. Discrete is like numbered, like either A or B. There's no term in between.
So which one of these is discrete random variable?
The shoe size.
Yeah, shoe size. I think date of birth is yeah, I think discrete as well. I think it's 2 and 3. Very good. Do you know how to find expected value from this distribution here? So what this means is that there is 10% chance for 0 showing up, and there's like 30% chance of 2 showing up, etc.
Expected value, you times them all together and plus them together.
So 0 times by?
0.1.
0.1 plus?
1 times 0.2.
1 times by 0.2, that's right. So etc., right?
Yep.
So I think that was, let's try this. 0 times by, so that's a 1 times by 0.2 plus 2 times by 0.3 plus 3 times by 0.2 plus 5 times by 0.2. Is that right? So that's equal to 2.4. That's the average value. How do you find the variance?
Variance is e to power x squared bracket e to x all squared.
So how do you find the so we know the average is this one. So how do you
So that's average. So you square 1 you square 1 to the power of 2, 2 to the power of 2, 3 to the power of 2, and then you times it by PR of x.
Yeah. So this is how you do it, right? So bracket 0 times by 0.1 plus.
Plus 1 squared times 0.2.
Yep. Plus
4 times
4
0.3.
times by 0.3 plus
Plus,
9 times by 0.2, right?
yep, etc.
Yep. And then plus 25 times by 0.2, right? So that's this one here.
Sure.
That's 8.2. Could you tell me how to find the variance, please?
And then you 8.2 minus 2.4 squared.
Yep, very good. That's equal to this one, 2.44. That's the variance. Very good. Now let the random variable x have an expected value given by mu and standard deviation given by sigma. The mean and standard deviation for the random variable z. So that's the z equals to. So you know this formula, right?
Yeah.
So what do you think is the answer for this multiple choice question?
Hang on.
So what it means is this: when you have the z-score, what's the mean of the z-score, and what's the standard deviation in z-score?
Z-score is the measure of the spread.
No, z-score is standard variable. It's the standard variable. So you know how when you have some distribution, for example, when you may have a distribution with an average of 170 and the standard deviation of 10, true? So this is a random variable x. But any distribution can be converted into z-score. Is that right? Now here's the thing: z-score always has mean of how much?
Mean of 0.
0. And what does 1 mean?
1 is one standard deviation, which
1 is 1. So that means standard deviation in z-score is 1, isn't it? Because one z-score of 1 means 1 standard deviation. So the standard deviation must be 1. So the question here is, the answer is this one here.
Okay, so no worries.
Question 6 here. What is in a test, about 95% of the scores are between this and this, so you can figure this one out yourself. Which one of these is a binomial distribution? Is not a binomial. Bernoulli is binomial.
Okay, yep.
Which one of these is not binomial?
B.
B is not, right? So that's all good. Everything else, it must be either a success or failure, right? So tossing coin, that's head or tail. Tossing coin, it's either head or not head. Dealing cards, replacing and repeating, recording the number of aces, so it's ace or not ace. Defective or not defective, so that's why these are all binomial. Let's have a look at this one here. 10. A fair die is tossed 5 times. Do you need to know binomial distribution?
Yes.
Yep. So what's the answer for this one? What's the probability of obtaining exactly
So
1?
It would be 5 times by 1/6.
No, that's not right. So it's a 1 on 6 to the power of 1.
Oh, okay. Times 5 times
5 on
6 to power 5.
So this means you'll get 1/6 and everything else, right? The remaining 5 can be anything else. But you need to times this one by. You're tossing it 5 times, right? Oh, hold on. This is actually 4 here.
Oh, yep, that's true.
Yep. And you need to times this one by 5C1. So you see that the probability can be 6 here and something else, something else, something else, something else, you know?
Mm-hmm.
Something else and the 6 and something else, something else, something else, right? So when you do 5C1, you're trying to figure out how many ways you can place your 6.
Mm-hmm.
Do you understand?
Yep.
So how many ways of choosing one of them as your 6?
Mm-hmm.
The answer is there are 5 ways, and this is probability for getting 1 6 and probability of getting 4 other values. So that's equal to this much, which is that one there. So let's take a look at the answer. 0.4018. Is that right? 0.4018. Yep. So if I check the answer, question 10. Yep, it's right there. So let's move on to the next question.
These are pretty simple questions.
Yeah, they get a little bit harder, you know, as you go. So I think I'll leave this question to you.
Mm-hmm. Maybe we should go work on sampling because I'm struggling for that.
Sampling, all right.
Mm-hmm.
Are you still using the yellow book?
Yes. It's chapter 15.
Yep. These stuff here. 15, yes. Okay. Have you tried any question here in the review section?
Not for chapter 15. I've tried chapter 13 and 14.
Okay. You want to try 15 now?
Mm-hmm.
Okay. So these are the formulas, okay? So the proportion is P,
Mm-hmm.
and the standard deviation of the sample proportion distribution is given by this quantity here.
Mm-hmm.
Now, this is known as margin of error, and you can use this formula to figure out how many samples you need to get, okay? So margin of error is given by this. We'll have a look at this later. So question 1. So company has 2,000 employees, 700 are female. So that's the true population proportion, okay?
Mm-hmm.
So it's a 7 out of 20 is the true population proportion, which means that's the answer.
Mm-hmm.
A random sample of 100 employees was selected, but 40 of them were female. So you get, so the true answer is 7 out of 20, right? Which is equal to about 0.35.
Mm-hmm.
But then you did your survey, and the 40 out of 100, which means 4 out of 10, true,
Mm-hmm.
was your result. So what is the population? That's 2,000, right?
Mm-hmm.
Population is 2,000. What is the value of the population proportion, P, which is 7 out of 20? What's the value of the sample proportion, which is 40 out of 100? That's very easy, right?
Mm-hmm.
We're going to move down to something harder, like, for example, we're going to look at this one here. 7, a newspaper determined that an approximate 95% confidence interval for the proportion of people in Australia who regularly read newspaper news online was 0.5 to 0.7. So here's the idea. So I'm going to capture this. So you take some sample size n. So we don't really know how much this is, okay? So you ask some people, all right? Now, here's the thing. The more number of people you survey, the narrower this confidence interval will be.
Mm-hmm.
So for example, if I ask 100 people, and then I found 60 people read newspapers, then what's my proportion?
Mm-hmm.
So 6 out of 10, is that right?
Mm-hmm.
Then based on that, I can plot this distribution of samples. So I only did one survey, is that right?
Mm-hmm.
And I found this the answer to be 60% of people reading newspaper. Does that all make sense?
Yep. So the mean will be 60.
Well, we no longer talk about mean. It's no longer mean, okay?
Mm-hmm.
It's no longer mean. We are now talking about proportion.
Okay, sure.
Okay? But here's the thing. How you surveyed 100 people, and out of that, only 60 people answered, and this only gives you one value of the answer, right? One single valued answer, doesn't it?
Mm-hmm.
We're not getting distribution of 100 people from this single experiment, from this single
that's true.
surveys. From this single survey, 100 people were involved, and this gives you 0.6, and that is a single answer. Now the question is, how do you get a distribution like that? See?
Mm-hmm.
Because this one here is just one, giving you one data point. How do you get a distribution like that with a standard deviation of, well, that is equal to P1 minus P over N. So this is equal to 0.6 here and then 0.4 here over how much? 100. If I do that, it's a 0.6 times by 0.4 divided by 100 and take root of that. That's equal to 0.048499, 0.0490, like that.
Mm-hmm.
So here's the question. You only got this one data point. What is that distribution all about? What this one is about? This one is a it's a guesswork of predicting what predicting how. So let me just write this down. Can you see this writing? The distribution is an approximation of how the sample proportions would be distributed if the survey was repeated many times. Okay? So I asked 100 people, do you read newspaper? And 60 people answered, and it gives me 0.6.
Okay.
Now, if I ask another 100 people, and some of the people who were included in the previous sample could be actually in here as well, because I'm doing a random sampling, then that could give you 61 people. Then this will be 61. See?
Mm-hmm.
0.61. And then if I ask another 100 people, then it could be 50 people reading it, true? So then you get lots and lots of these data points. You are kind of approximating this.
Okay, so the most abundant is what creates a
Yeah, so of course the most abundant one is around your mean. Mm-hmm. And you are approximating the distribution of this. Listen very carefully. This is distribution of sample proportions. You only calculated one proportion, but you are kind of approximating what the distribution of the proportion would look like if you were to repeat all of this this sample here, this experiment many times.
Okay.
Understand?
Yep.
Yeah. So some of the proportion will be here, some proportion will be here, so they will be distributed. Now, imagine this. So I asked 100 people, right?
Mm-hmm.
What would the distribution look like if I have 1,000 people? So, for example, if I only ask 10 people, then out of 100 people, out of 10 people, it could be 2 people reading the newspaper. It could be 7 people reading newspaper. It could be 9 people reading newspaper, 10 people reading newspaper, right?
Mm-hmm.
So it's going to have a very large distribution, you know?
Mm-hmm.
Sometimes here, you know, very large distribution. But if I ask 100 people, then sometimes it's 51, sometimes it's 52, sometimes 53, sometimes it's like 60 people, but not like 20 people, you know. This 20 out of 100 is not likely to show up, you see?
Okay, true.
Yeah, because this sample is such a small number that if you were to ask if you were to calculate the sample proportion based on that value, it's
Mm-hmm.
really going to be not that accurate. But if I ask 1,000 people, then the proportion would really be consistent, you know,
Mm-hmm.
because you're asking a lot larger number of people. So
Mm-hmm.
the distribution kind of becomes much narrower. Do you understand?
Okay, yeah, because it's more.
Yeah, you're actually asking more people, so they sort of average out. Any anomaly or any extremes or any outliers can sort of blend in and can be neutralized, if you understand.
Yeah.
Yeah, so that's why the standard deviation of the sample proportions actually
Mm-hmm.
depend on this n here. So the larger the value of n, the
Mm-hmm.
smaller the standard deviation. Do you understand?
Mm-hmm.
So
Sure.
here's what we do. So based on 100 people, 60 people said I read newspaper, and based on that, I figure out this standard deviation. That
Mm-hmm.
means if I times this one by 2 and add it on to this one here, so I'm going to say this is 0.05, okay? So twice this one is 0.1, isn't it?
Mm-hmm.
Then I get 0.7. And if I times this one by 2 and then minus that from 0.6, then I get 0.5. Is it right?
Yep, that's 4 standard distribution.
This is 2 standard deviation.
Oh, yep, sorry.
And this is the 95% confidence interval. So here's the thing. What was the value? So by coincidence, question 7, they didn't tell us how many people they asked, right?
Mm-hmm.
But I kind of just guessed that this is 100 people. This is just lucky, you know.
Yeah.
And then I figured out the 95% confidence interval to be between 0.5 and 0.7. Is that right?
Mm-hmm.
So this is asking what was the value of the p which was used to determine this confidence interval? Well, it must be halfway between these two, true?
Yep.
There must be 0.6. That's the answer. What is the margin of error? Well, the equation for margin of error is this one here. So let's figure out what this is. All right. So let's plug in 0.6 here, 0.6 here, and then hold on. Yeah, we need to figure out n, obviously, to find out what the margin of error is.
N is the trials, right? How many people we ask?
Yeah, how many people we ask. So C is very simple. How could the newspaper increase the precision of their study? The answer is ask more people.
Yep. Is there any other way?
No, this is the only way.
Mm-hmm.
And also ask more people from more broad. What is it?
backgrounds.
Yeah,
More
broad
diversity.
backgrounds. You don't ask people who like 1,000 people from like one particular ethnic group, then obviously you're doing a biased study.
Sure.
Yeah. So this question here. So this equation and this equation. So have a look. So it says distance between the sample estimate and the points of the confidence interval is called margin of error. And for 95% confidence interval, so we kind of worked that this is 100, isn't it? So let's see what happens if this is if we plug in 100 here and 0.6 here. Okay. So we just want to understand.
How do we figure out it's 100 though?
Well, we haven't figured it out yet, but I'm just trying to make you understand this one.
Okay, sure. No.
So I'm just going to plug in 0.4 here. I'm going to tell you how you work out 100 later, okay? And that's using this one here. And this one is 100. And then times by 1.96. And you get this one here. This is the margin of error. Let's actually have a look at a chapter that has the margin of error there. Yeah. So here's a question. It says, determine the sample size required to achieve a margin of error of 2% in an approximate 95% confidence interval. Let me have a look. So this was 0.7. Margin of error of 2%. Okay, I understand what that means. Okay. Yep. So margin of error means this. So, you know, we figure out that this is so 0.5, 0.7, right? So this is a 0.6 here and 0.7 here, 0.5 here, true? The distance from there to there is how much? 0.1, right?
Yeah.
Which is 10%. That's margin of error.
Yeah.
That's margin of error. So what is the margin of error? Must be 0.1 because the 0.6 is in the middle, see? And then you see the distance between this and this is a 0.1 or 10%, true? Now, using the margin of error, we can figure out the n, true? That's the sample size. So look, I'm going to actually use so if you flip this equation, you get this one here. Do you understand? So I'm going to actually use this one here. So I've got n equals to, so have a look, n equals to 1.96, and this 1.96 is used when it's a 95% confidence interval.
Okay, sure.
So you see, this is to 95% confidence interval, right?
So it just means 2 standard deviations.
Two standard deviation is exactly actually a 1.96 standard deviation. That's the 95%. That's the so usually 95% confidence interval is, we say, 2 standard deviation, but that's actually 1.96 standard deviation. So because we are told that this is 95% confidence interval, that's why we are using this number here. Understand?
Yep.
And then we divide that by 0.1, and then square, and then 0.6 times by 0.4. So let's see what we get from this. So it is 1.96 divided by 0.1, and then square it.
I got 92.19.
0.6 times by 0.4. So that gives us about 100 people, right? So that's what this is giving us.
Yep.
All right. So that's how you do question 7. All right. I think we should call it a day.
Sure.
I'll give this paper to you.
I'll do the practice test. I haven't got it yet. I'll get it done before our lesson tomorrow, which is at 5.
Yeah. So I'll send this to you now, and just book a lesson tomorrow.
I've already booked it.
Yeah, sure. 5 tomorrow. Do you want to come to my office or do online?
Probably to your office because I'll be writing over the practice test.
Okay, sure. I'll see you at 5 p.m. at my office. Okay, the new building.
Oh, okay. At the new building now. Okay.
Yeah.
Nice.
Daniel, which one is it?
First one.
First one.
Yep. Thank you.
All right. See you tomorrow.
See you tomorrow.